Okay. So for today, we're going to go over controlling beer off flavors. Now, this is a huge topic, absolutely a huge topic. And what my goal is to go a little bit further in depth with the topic for you guys, and then if we want to pull back a little bit or go a bit further, we can. We're going to talk about a handful of different options for this. I'm also going to give you guys a bunch of resources as well. So if you want to go further in any of these different areas, you can on your own time as well. So kind of got to go with like full how we can control the basic off flavors that we find in beer. Now, there's also off flavors that we find in beer that are not covered today. We're going kind of an 80-20 rule. We're going to cover about 80% of the most common ones. Sound good? Sweet. Okay. So with that, we're going to jump in. So there's a handful of different resources I want to just kind of link to off of this. So there is a controlling beer off flavors webinar that Richard, one of my business partners, did a while back. We also then have blog posts on a handful of these. So if anyone wants to go and find more information on these, this is one of the best places I recommend you go. We have, if you want on fusel alcohols, called Avoiding the Dreaded Cheap Booze Flavor. Acetaldehyde is just acetaldehyde blog post. Diacetyl, we have the forced diacetyl test. There's a sulfur blog post coming in a few weeks. But we're going to approach everything today in a bit less technical. If you want to find out, like, how much NADH is required to break down a diacetyl, like we have that in the blog post. So you can go deep into it in those zones if you want. So what I want to talk about first for this is just kind of why yeast cells do this, or why do the cells produce these things that we don't like. And I'm going to be asking you guys a bunch of questions, by the way. I don't like this. Just tends to be how I operate. It's a bit more conversational based. Do yeast cells know we exist?
Getting philosophical pretty early. Do yeast cells know that we exist?
Yeah. Are they trying to make us happy? Are they trying to be vindictive towards us?
The output is making me happy right now.
Yeah,
They
I
just
think
care
we
for themselves.
know
they
because
don't know.
we
So,
all
yeah.
have our own microbial communities that are unique inside of us, and the different balance contributes to like the gut brain axis, which is tied to
Yep,
serotonin and all kinds of stuff like
absolutely.
that.
So we rely on these organisms, but they don't from a like sentient standpoint, they don't know we exist. So whenever they do something that we don't like, it's not because they're mad at us or they're happy with us. It's because they're completely selfish. When something goes wrong, it's because they're doing something that they had to do. They're trying to do something to survive. They are making a decision that is the best thing for them. So we're going to just kind of do a quick little walkthrough on this. So acetaldehyde is one of the most common off flavors you see. That's that kind of green apple tone. We'll talk about that in a second. Can anyone think of another aldehyde that we see in common vernacular in society? Like okay, say an aldehyde. Like what's another aldehyde that comes to mind?
Rubbing alcohol.
That's an alcohol.
Formaldehyde.
Okay.
Formaldehyde, yeah.
Formaldehyde. Now, is formaldehyde toxic?
Yes.
I think so.
Yeah. In
Yes.
general, this is a general statement. In general, aldehydes are very toxic compounds, not just for humans, but also for yeast cells. So I like to use it as kind of a touch point for you guys to help us understand how the yeast cells are operating. If the beer has acetaldehyde, that means that the yeast cell has produced something toxic, and that was the best option for it. That means that we put the yeast cells in a situation that was very negative, where their best case situation was to produce a toxic compound for them and us. That's not good. They don't want to produce this stuff. They want to produce something easier. But what we've done when we have acetaldehyde issues, we've kind of done something negative to the cells that's forced them to make this stuff. Now, we'll keep going through this. Fusel alcohols are a similar idea. Fusel alcohols are, the yeast cells didn't have the energy to break down this toxic thing. Now, is alcohol toxic?
In high enough quantities.
Yeah, high enough quantities. It's mildly toxic across the board. Like, it's toxic to us in minimal and higher quantities. Doesn't matter how it is, but it is toxic to us to a certain degree. Fusel alcohols also are toxic. Now, fusel alcohols are larger molecules, are kind of those more hot, boozy alcohols, the ones we find in like Russian imperial stouts, barley wines, some Trappist beers. If you get the alcohol burn, it's usually associated with fusel alcohols. Diacetyl is a similar thing. It's the yeast cells don't want to produce this. They're trying to do something else. We'll talk about it soon. And then you even get things like hydrogen sulfide with sulfur chemistry. Hydrogen sulfide is a noxious gas. It's toxic. It actually inhibits a bunch of enzymes that are required for cellular metabolism. Like whenever the yeast cells are producing these things, they don't want to make them. They really don't. But what we have done as the brewer is we have done something to them, whatever that something is. And that's what we're going to be walking you guys through today. We have done something to them to force them to make this stuff, and we should kind of feel bad about it because we have not been good yeast farmers. And that's kind of the background I want to put forward. Like, we should not blame the yeast cells for making bad beer. We made them this way. We forced them to do this thing. It is on us. They did not, we are the one that put them in this stressful situation or terrible situation. They're just reacting to it. Don't blame your yeast cells. You got to look at yourself. This is a big issue with pro brewers, by the way. This is a huge issue with professional brewers where they get mad at their yeast cells. Like, you should not get mad at your yeast cells. All right. So we're going to break down this few acetaldehyde, sulfur, fusels, diacetyl, and phenols. We're going to start jumping and going through kind of one by one. But before we do that, I want to kind of just give you a framework for this. And we can talk about this in a few different ways or use analogies for it. But whenever you're looking at an off flavor or any sort of issue, you kind of have two levers you have to work with. You can either make less mess or get better at cleaning. So like, you can think of this like if your house is dirty, you can either focus on trying to prevent the messes from recurring or just get really good at cleaning your facility. If we're worried about having diacetyl issues inside of a beer, we have two options for it. We can either focus on preventing diacetyl from being produced, or focus on maximizing the reuptake of the diacetyl that once it has been produced. Focusing on only one is pretty foolish. We need to be focusing on both. So when we're walking through each one of these two, I'll be using this framework. I'll be talking about how can we maximize the reuptake, but more importantly, in my opinion, how can we reduce the creation of the off flavor. Those are the two different levers we're working with. And for those who kind of want a TLDR for all of this, here it is. TLDR stands for too long didn't read, by the way, because I know that sometimes we start getting technical and things like that. It becomes overwhelming. Also, this is like a teaching thing for me. One of the reasons I try to ask you guys questions is if I say Charlie Brown, do we all know what the teacher sounds like in Charlie Brown? Wah, wah,
Wah,
wah,
wah, wah,
wah.
wah.
Yeah. So usually the average human has about a 10 minute attention span, where after 10 minutes you start sounding like Charlie Brown. But if you have some sort of interaction or like some sort of back and forth for it, it extends almost indefinitely. So if you want, we're at probably about like a 5 to 10 minute point at this point. This is your TLDR if you're losing attention or you're just like, this is too much. The cheat sheet is acetaldehyde is usually a lack of zinc and oxygen. Sulfur is usually a lack of certain amino acids, mainly being cysteine and methionine. Fusel alcohol it's kind of the Goldilocks thing, either too much or too little fan or not enough oxygen. Diacetyl is too little protein or too low fan, or too little oxygen, and phenols are an outlier. They're a completely different outlier. So we'll go further in it. So acetaldehyde, this is a weird one. What is acetaldehyde? Acetaldehyde is commonly described as having this green apple flavor to it. Now, who's ever actually tasted the green apple flavor? Okay, let me rephrase the question.
In beer, or just like I had a green apple in my life?
Oh, no, in beer. In beer.
Definitely, yeah.
Okay, so who's ever had this green apple flavor in a beer that was not a lager? So this is one of these points where the context for where the research is done and how it's described becomes really important. All the research around acetaldehyde is done in light lagers. It's all been done by Molson, Coors, those big guys. So when you start looking at it for, let's say, English style pale ales, American style pale ales, things like that, the flavor descriptors actually don't match. So a lot of people will think they have some sort of weird flavor, and they're actually dealing with aldehydes. They just don't know how the vernacular to describe it. So if you ever get kind of a weird flavor and you be like, there's something off. It's not diacetyl, it's not DMS, it's not any of these things, but there's something off. It's probably this. It's just probably not a light lager, and that's why you can't figure out what it tastes like. That's usually what it is. Now, some of the ways in which I've seen diacetyl, I've experienced acetaldehyde tasting are everything from freshly cut pumpkin or gourds. Overripe fruit is a very common descriptor for this, like rotting fruit or kind of like your, I don't know, you have green bins there actually? I don't know this. Yeah. Like green bins, like just your compost bins.
Yeah.
So we'll describe it as freshly cut grass, cut avocado, paint thinner, and solvent. Excuse me, at very high concentrations. Either way you put this, it's not a good compound. It's not good. But it's not always just that, quote unquote iconic green apple. It often materializes in pale ales and IPAs as one of these flavors. It's not always just green apple. Now, the way it's formed is actually pretty cool. And now this is, I think, one of the most technical diagrams. We'll go through the entire talk, but it's also, I have a favorite image, like favorite metabolic pathway, because that's the person I am when it comes to fermentation. This is my favorite metabolic pathway. I want to kind of walk through it for a quick moment. So what we have here is glucose. This is all the sugar that enters the cells or all the different yeast cells. This glucose gets converted into what we call pyruvate. That's one of these kind of intermediary states inside the cell. This pyruvate then gets broken down to acetaldehyde, which then acetaldehyde gets broken down into alcohol. This is how yeast cells produce all of the alcohol that we then consume in beer, wine, cider, sake, spirits, whatever it may be. There's a few things I want to highlight here. So we go from glucose to pyruvate, and we generate 2 molecules of what we call ATP. Now, if anyone remembers like high school or early university, ATP is energy that powers everything. That's all we got to know for it. That's as deep as we're going to go. But we need this. That's the thing that's the reason this entire process occurs. Now we got this pyruvate that breaks into acetaldehyde, and this is one of the moments where one of the reasons I really like this image. What we see CO2 be produced from pyruvate to acetaldehyde. So metabolically, where do you think the CO2 that we see rising through our fermentations comes from?
This step.
It's right there.
Yeah.
It's that step. Like this is the step where about 95% of all the CO2 that we see come off out of our yeast cells and come out of our tanks, our carboys, whatever your buckets, whatever you're using. That is the metabolic step where it comes from. Which the first time I saw this, I was like, that's just really cool. I think that's really cool. So that step right there. Now, this acetaldehyde then gets turned into 2 molecules of ethanol. This is where we got to take a little side step and explain something. So you'll notice in the center we have this cycle of NAD, which then gets converted to NADH, and then NADH gets used to break down the acetaldehyde into ethanol again. Overall, this process from glucose to ethanol is NADH neutral. It's 2 are produced, 2 are consumed. 2 are produced, 2 are consumed. It's really important to emphasize this, that NADH is like concentrated ATP. It is concentrated energy. Like 1 molecule of NADH is worth a few different molecules of ATP. So if you ever find yourself looking at metabolisms for yeast cells, this is a daily occurrence for myself, but I know this is not a common thing. Whenever you see the yeast cell spending NADH, that means that this is really, really important. Really important. And I want to kind of illustrate this. We have 2 molecules of acetaldehyde. And what do we know about aldehydes when it comes to cell health? Do yeast cells like them or not so much?
Not good.
Not good. So we know the yeast cell doesn't like them because we see them willing to spend 1 molecule of NADH in order to break them down. Each. Whenever we see the yeast cell or a human in particular, humans as well, whenever metabolically we are looking to spend NADH on something, that usually means we are detoxifying the environment. We are removing something that is poisonous to the organism. Usually a big deal. Usually a big deal. So that's just one of the things I wanted to kind of emphasize for this. Is that, whenever we see the yeast cell using ADH, it's going to come up 1 or 2 times throughout. That indicates that this is a really big issue. Now, the other part for this that's really important is this enzyme we have here called alcohol dehydrogenase 1. Now, fun fact, you have all of us have a version of this enzyme inside of us as well. It's kind of neat. So for yeast cells, they take glucose to pyruvate, pyruvate to acetaldehyde, acetaldehyde to ethanol. For us, we then take the ethanol, break it down to acetaldehyde, which then we urinate out. And whether or not it is the creation of the ethanol or the breakdown of the ethanol, it is this enzyme here. We both need it. Yeast cells need it, and we need it. It works in one direction for yeast cells. It works in the opposite direction for us. But same enzyme. It's kind of neat. Now, in both of our cases, yeast and humans, this enzyme here is what we call a metalloenzyme. And in this case, it is a zinc catalyzed enzyme. See this little zinc molecule right over here on the right-hand side. Zinc is really important. This is one of the reasons why, zinc is important for your health. There's a lot of enzymes that are in your body that do the things that allow you to do all the things that you do that require zinc in order to function. Same thing goes for yeast cells. There's a lot of these enzymes that require zinc in order for them to function. So I'll give you, what do you think is going to happen if this enzyme does not have zinc? You can be wrong, by the way. It's okay. You can guess. I'm not going to judge. Like the other people in your club might judge. I'm not going to judge you.
It's not going to work.
Yeah, it won't be converted, right? So and then it produces off flavors.
It will produce some off flavors. To the statement of it won't work, it will kind of work. It will kind of work. Think of it like a car that needs an oil change badly, really badly. We're gonna start seeing the fuel consumption go up. It's gonna shake. It's not gonna work as properly. It might get more damaged. Like instead of getting, I don't know, what does my car get? 40 liters, but 400 kilometers, whatever that is, but 10 kilometers a liter. It might get 6 kilometers a liter. Like, you can start looking at it. The enzyme becomes far less effective. It becomes more difficult to run. So this is where we start having issues with acetaldehyde problems. Acetaldehyde problems can be one of 2 things, typically. We said already this NADH molecule here. In some cases, NADH can become lacking. That's one of the causes of acetaldehyde is if we start having a lack of NADH, usually due to a lack of wort aeration, which we'll talk about at the end. The other thing it can be is just not having enough zinc. If we don't have enough zinc, this enzyme, this machine, it's hard to run, and it just won't run well. And the end result is that we'll have a yeast strain that wants to break all this stuff down, but does not have the machinery to do it.
If you don't have enough zinc, your yeast health will stink.
I might take that. It's actually pretty good. Yeah, if you have either of these things, we're gonna get acetaldehyde issues. Now we'll talk near the end about how to, or kind of different points as to how to do that. Now, if you want to maximize your wort aeration, this is mainly for a pro brewer standpoint. I'm curious about this one. Who aerates their wort?
All the time.
All the time?
Yeah, every time I brew, for sure.
Okay.
Yeah, same thing. Especially in lagers.
Yeah,
especially lagers. Okay.
Lagers, big beers, actually every beer, but
yeah,
longer and lagers and big beers for sure.
Okay, cool. So I'm excellent. If for those who don't, it is okay. I'm going to explain at the end an easy way for you to aerate your yeast cells and not your wort. We'll get to it. You don't have to necessarily always aerate your wort. You can just aerate your yeast. Now, if you want to maximize acetaldehyde reuptake and things like that, and it's reduces its creation, you need proper wort aeration. If you want to find more information on wort aeration, you can follow the links, and I'll send everyone the presentations on this, by the way, so you guys can have all the links and everything, all that stuff to it. You can follow the link, and it will bring you to the one of our blog posts on wort aeration. You can go through the whole thing there, but it's kind of outside of the scope of what we're covering today. Now, when it comes to how to get more zinc, this is complicated for the home brewer if you want to go on a commercial scale. So I don't suggest you do. I don't think it's going to make a lot of sense for you. There are a few issues with zinc, and this is what we got to kind of emphasize. There is lots of zinc in your wort. Sorry, in your malt. Like in the malt, the kernels itself, there is tons of zinc. Like it's should be more than enough. The issue is that as we get our hot break and our cold break, so as we're producing our trub during our boil, it all comes out of solution. It all falls out. And I don't mean like 70% or 80%. It's about 99.5% of the zinc falls out of solution. It's a ton of it. Like it's functionally all of it. Now, there are other issues with this. One of the things we've seen just globally, like worldwide, is that zinc levels in grain have been decreasing precipitously over the last 30, 40 years, to the point where one of the biggest issues in Australia is that if you get any sort of barley grown in Australia for brewing, it has functionally zero zinc to begin with, just because the soils there have almost none of it naturally inside of the soil. So this can become a problem. The easiest way for us to add more zinc is through things like yeast nutrients. That's the easiest way for it. That's one of the ways, like if you look at almost all, I'd say the higher quality ones, which I'd say that ours is, they all have a backbone of a zinc enhanced or a zinc enriched yeast extract production. Yeast extract produced in a zinc enhanced environment. And that's one of the biggest things that makes a brewing yeast extract unique from, say, a pharma or food yeast extract that would be used in, say, other industries, is this zinc concentration that we need for it. So those two things, if we can increase our wort aeration, that'll go a long way. Got a hand up.
Yeah, so when you say most of the zinc gets lost during hot and cold break,
yeah,
when would you suggest to add like any kind of yeast nutrient?
Great question. Okay, so the benefit of zinc enhanced yeast extracts is that because it's not just ionic zinc, and if I lose anyone, just let me know. Because it's not just free zinc kind of floating around in the wort or in the water like we have with like magnesium, calcium, things like that. It's bound zinc. The zinc is already inside of enzymes or inside of dead enzymes inside the yeast cell. So it doesn't precipitate out in the trub. It's already inside these yeast cells, these dead yeast cells that make up the yeast extract that we're adding to the wort in the form of, say, yeast lightning or yeast extract or like Cerevomyces from Lallemand or things like that. Like those are all the zinc is there is not free ionic zinc. It is bound to something else, so the yeast cell can easily consume it, absorb it, and it won't go into the trub. I don't know if I don't know if that makes sense.
Somewhat.
Okay. Yeah, you can kind of think of it like no, it's a bad analogy actually. Never mind, that wouldn't work. It's no, that wouldn't explain it. It explains it, but you need some biochem background, which is not a fair thing to talk about in this group. Whenever zinc is just kind of free in solution, it's much easier to kind of like zinc is a positive charge. So whenever you have any sort of other negative molecule, say a negative protein inside a solution, it will bind to it, and then that is what's going to form your trub. Because the yeast extract we're working with is already part of larger molecules that are very soluble, and they're not able to have those interactions with molecules that would make up your hot or cold break to fall out. They stay inside a solution. Like they have carrier molecules with them is almost a way to look at it. Make sense? Ish? Make sense enough?
Yeah.
All right. Now, one other place we see acetaldehyde come up is hop creep. I want to kind of just get a pulse for the room. Do we all know what hop creep is? Does anyone not know what hop creep is? Excellent.
I'm very new.
That's fine. That's fine. Absolutely fine. I teach at Niagara College for the Brewmaster program. I get a bunch of students every single term who have no idea what's going on. It's all good. So hop creep is this phenomenon where the enzymes, it's just like the alpha and beta amylase we have in our malt. A lot of hop pellets will have what's called glucoamylase, which is like those two enzymes that breaks down starches and dextrins into simple sugars. Now, the issue is that these things start activating, so the issue, after we dry hop the beer. So our yeast cells are done fermenting for the most part. We dry hop the beer. We now have, these simple sugars being produced from any sort of dextrins or like small amounts of carbohydrates that were left over inside of our wort. The yeast cells start to re-ferment them, but now they're fermenting in a stressed environment, high alcohol, low nutrient environment, and they produce acetaldehyde. So we have had a lot of commercial breweries have this issue. I was actually judging a competition a few weeks ago, and there's 2 or 3 of the beers in the flight that had this in spades, and it was unfortunate because like beyond that acetaldehyde, it was a great beer, but it had this glaring issue with it, which is probably from hop creep. So yeah, the biggest issue, the biggest way you can help avoid this is with some yeast nutrients. Yeast nutrients will fix this, especially zinc. If you want a good resource on this, and I try to give you guys as many resources as I can to help you guys, like if you want to go down rabbit holes, I like to send you down the rabbit holes so you can kind of go to your heart's content. There's a podcast called Beer and Brewing Podcast, episode 300 with Vinny Churzo of Russian River Brewing Company, who's kind of like one of the godfathers of IPA brewing in North America. And he goes through a whole spiel. It's like a 2-hour podcast, so you gotta wait for it. But he goes through a whole spiel about like what the impacts how they've accounted for hop creep and what they've done to make sure it goes smoother and avoid the off flavors and all. It's good stuff. If you want to go through that. Which then brings us to sulfur. So are there any questions about acetaldehyde before we go a bit further? Awesome. Okay. So sulfur is not a good compound. It's not a compound that we want in the beer. It's a compound that the yeast cells want in the beer. No one wants it in the beer. So let's talk about how it gets there. So this is a group of compounds mainly made of hydrogen sulfide, or H2S. Excuse me. It smells like rotten eggs or sewage, which is not pleasant. Sometimes, so there's also other molecules called carbon disulfide. This can have a garlic-like aroma to the beer. So if you ever get garlic off a beer, this is probably what you're dealing with. As an aside, there are certain hops that are known to also have kind of a garlicky tone. It is a different molecule than this. It is also a sulfur compound, but it's a different molecule called allicin. Certain hops like Summit are known to have that flavor inside of them in bad years. And there's also mercaptans. These are kind of skunky, burnt rubber. None of these are really pleasant. None of these are things that we really want to have in there. And H2S out of all these is the most common. It's kind of rotten egg tone is by far the most common. So if you want to understand why it happens, we can talk about it if you want to. Sulfur from your water profile. So SO4, which is a commonly found substance, not just in your water, but also in your malts, also in your hops. It's going to be present in the beer no matter what. This will get turned into SO3, which then turns into sulfide. And then what's going to happen is our yeast cells are going to try and make what we call 2 amino acids, cysteine and methionine. Now, these are essential amino acids. If anyone, have we all heard the term essential amino acids before? Or amino acid before? Okay. So amino acids are the building blocks for your cells, the thing that allow your body to heal, make proteins, make enzymes, do all the different stuff. And so 2 of them that require sulfur are cysteine and methionine. Now, if your body's trying to produce these enzymes, trying to produce these 2 amino acids, but something's going wrong, something's not working, the yeast cell is still processing the sulfur and it has to get rid of it some way, shape, or form. And the way it does that is it starts producing H2S, or this rotten egg tone. Now, the solution for this, if you want to get from like a biochemical standpoint, is to just give them more nitrogen. It is to give them the other building blocks they need in order to produce this compound. That's the easy solution for it. Is if we give them more cysteine, methionine, or more base ingredients, everything else flies through and we don't get this compound. If we want to try and reduce the creation of it, give the yeast cells more FAN or free amino nitrogen. The thing we do protein rests for, or through the different protocols we can go for it. But yeah, it's typically a response to the yeast cells not having enough environmental nutrients. It's like not having enough protein in your diet is a way to look at it. You start getting egg farts is a way to look at it. So yeah, it's not something we want to do. It's not something the yeast cell wants to do. And one of the ways we can tell the yeast cell doesn't want to do this is what we see on the left-hand side. So we see we're going from sulfates all the way down to cysteine and methionine. And you look right in here, we have NADPH to NADP, which is similar to NADH to NAD, just like we saw with acetaldehyde. This is a very extremely high energy consumption protocol. It requires a ton of energy. And the yeast cell would rather not do it. It's only going to do this if it has to, if it really has to. It would prefer not to. It would prefer for us to just give it the stuff up front and not have to worry about it, which is typically how we see us handle it. So if you are getting a sulfur tone instead of a beer, typically this has to do with a fan issue, not having enough protein instead of your wort. Now, in the case of how we can actually add more fan or add more protein, I'm going to sound like I'm beating a dead horse on this, but adding yeast extract will fix this. Adding yeast extract fixes most off flavors, by the way. That is one of the best things you can do. It's one of the reasons why I can say this, like, we have spent years developing a yeast extract for our own protocol, and like all the yeast extracts that we sell, we use in our own process for making the yeast cells to begin with. And we've put a lot into them, and this is the reason why, because they just fix so many different problems. But other things that can cause sulfur is slow fermentations or lager fermentations. Very cold fermentations will also fix this. So also cause this. If you really underpitch your yeast cells, so like or use very old yeast cells, this can also cause us to get a sulfur tone inside of the beer. And if you have excessive trub carryover, especially hot break, this is a good thing. Do we all know the difference between hot break and cold break? We have newbies. We don't, right? So hot break is what is produced when we're heating the kettle. Cold break is the small particulates produced as we're cooling the wort. Hot break has almost no beneficial attributes to the final beer to be fermented with. Like if you ferment a beer with hot break, it's only going to damage the product. It has functionally no benefit to being present, but it will cause off flavors. Cold break, on the other hand, actually has a bunch of positive benefits to fermentation health and flavor profile development. So when I say trub carryover, I'm talking about hot break. If you have hot break coming into your fermenter, you can get sulfur. Cold break tends to actually clean up sulfur. But that's a much larger conversation. Much larger conversation. Any questions about sulfur? How we do it, by the way. I feel like I'm throwing a bunch of information at you. Is this all processing? Are we like, do we need to take like a break, like walk around, like do some breath work? I don't know. Vancouver, I don't know what you guys do.
Start doing some yoga.
Yeah, why not? You do you.
I think we're good. See
Whatever
thumbs
makes you
up,
happy.
Yeah, I think we're good.
Okay, wonderful. Cool. So we'll go with fusels. Now, I have been told by a bunch of people I know, and I'm frequently reminded by my students that I am more sensitive to fusels than most people. Who here is a BJCP judge? Is anyone?
We've got a couple on the call. LA and Rob are both judges.
Okay. So, cool. Okay, so we got a few. So yeah, when I was doing one of my grading, like judging tests for it, they gave me the two beers I was given for my judging were a Russian Imperial Stout and a Belgian Quad. Two beers that are known for having fusels. And I had to fight with the people who were judging it because like I wrote at the top, like, I taste these more intensely. I'm not going to be tasting like probably the things you are looking for in this beer. It just tasted like burning alcohol to me. That was it. And then they gave me a bad score and I had to fight them on it. It's like, look, I know I'm more sensitive to stuff. Eventually we sorted the whole thing out and did that part of again. But yeah, fusels. I do not like them. at all. So let's talk about how they're produced. So fusel alcohols are higher alcohols, or fusel oils, are that kind of hot burning alcohol. Now, if you've ever had like Smirnoff Red Label and it burns, or like Alberta Pure, or what's another really cheap alcohol, like cheap spirit, it doesn't matter which one, it probably has it. They have a high fusel content. That's why they're the cheaper alcohols. That's also why they burn and why they hurt, is they have a high concentration of these things. Excuse me. Now, in general, these do not taste good, but there is actually an evolutionary advantage for them to be produced, which we'll talk about in a second. They actually are the precursors for esters. Every single ester, so like the nice fruity, fruity characteristics we get off the yeast strains, they require fusel alcohols in order to be produced. So this is not ideal for them to be in this state, but if we can easily convert these into something else that's very, very positive. So when we're looking at fusel alcohols are kind of the incomplete esterification of compounds. Like, the yeast cell's trying to produce this nice ester, and something went wrong, and what we're left with is burning alcohol. It's not great. So let's talk about how it works. Yeah, fusel alcohols are a natural byproduct of amino acid synthesis. We're never, like, there is no way for us to reduce their creation other than simply giving them the yeast cell, the amino acid up front, which again, yeast extracts have all the amino acids up front. We can just give them that stuff and they don't have to go through this process. But other than that, there's no way to kind of change it. If we want to get into the weeds on it, if we do, the way which they're produced is we go with this process where we have amino acid. A process called deamination occurs, where this nitrogen portion is scrubbed off, it's pulled off. This thing gives us what's called an alpha keto acid, which then gets decarboxylated, or the CO2 gets removed, carbon dioxide is removed. At which point we have an aldehyde, which gets reduced into a higher alcohol. Now, I want to point out one thing beforehand. Alpha keto acids are incredibly toxic, like horrifically toxic. They're really not good. So the yeast cells, like when the yeast cell is fermenting, if they have any available energy, this is one of the first things they do to break down. Like it's like having I don't know, my mind's going to ricin. That's a terrible example. It's like having mustard gas in your house. Get rid of it. Like it's very, very bad. So the yeast cell will break all that stuff down first, which then leads us to aldehydes, which we've talked about aldehydes already. They are not good. They are toxic. So the yeast cell then tries to break down this aldehyde into a higher alcohol. We've broken down two really toxic substances to get to this less toxic substance. That's kind of where we're starting at with this process. Now, what do you think is healthier for the yeast cell? To have the amino acid given to them, or to go through this entire process? Just give them the amino acid.
Give it to 'em. Yeah.
Just give it to them. Don't make them do this. This is not nice. Not nice. Because when they have to make it, this happens. Just give them the amino acid. Just take care of your yeast cells. Your yeast cells and your beer will improve. It makes your life much better. Now, here's the issue. There's a bit of a Goldilocks thing here. If we have too much fan, we will get more of these higher alcohols. If we have too little fan, we will also get too much of these higher alcohols. Who's ever made like a Russian Imperial Stout with like an all malt Russian Imperial Stout, like an all malt barley wine, or like just really any beer north of 8% that is 100% malt? And how boozy was it?
So boozy.
It's so boozy. So one of the best ways you can control for, or one of the reasons that happens, is because the more ABV we add, the more malt we add, the higher the fan content gets, and we very quickly get past that, this porridge is too hot point for the Goldilocks analogy, and the result is booze. We're going to take a little, I'm going to peel away from the presentation for a second, and I'm just going to bring up a beer. Do we all know the beer Duvel, or Duvel, depends on how you say it? Can you guys see the screen, by the way, just to make sure? Yeah, okay.
Yep.
So does anyone recall what the ABV on Duvel is?
Isn't it like 8.5 or 9 almost? Or is it
There's
higher
different
than that?
versions of it, correct. There are some versions that are 8. There are other versions that are 9 or 9.5.
Yeah.
This is a brutally high ABV beer that is roughly 40% dextrose, 40% simple sugar. Now, the reason they do this is that if they make about a 5 to 6% beer, that locks in their fan profile. And if they were to use all malt, A, it'd be really expensive. But B, the fan content would get so high that they'd start getting infused with alcohols and the quality of the beer would detract. The reason this beer drinks like a 5 or 6% beer and not the 9% beer it normally is because they've controlled the fan levels. They've made sure that that fan has not become excessive. And in doing so, they're controlling their higher alcohol or their boozy characteristics of this product.
It's a beautiful beer, by the way. And I had like 3 or 4 ones, and then I looked at the alcohol content. I was like, whoa.
That happened to me as well.
It's happened to us all. It doesn't taste like how strong it is. This is actually how a lot of Trappist beers are made. Like one of the reasons why Trappist beers use a lot of sugar profile to them is because it allows them to get a lot of fermentability without having excessive levels of fan, which then controls the fusel alcohol profile. So if we reduce the amount of the fan we have by adding simple sugars for high ABV beers, we can knock down that boozy characteristic and make the beer not taste as hot and aggressive, which is a good thing. I think it's a good thing. Personally, I appreciate it. Personally. So yeah, and there are other things that we can use to control this. Fermentation temperature is huge. Like you can ferment. Like if it has, I don't know if you guys get this out here, but we have it in the LCBO. It's called Santa Claus. It's I think it's a 13 or 15% German style Doppelbock, something like that. Like it's a very high ABV Doppelbock. That is fermented just incredibly cold. It's fermented at like 8 degrees Celsius over like a 3-month period, and you can get it. There's almost no booze on it. But it's just because the fermentation temperature is so low that we can reduce the fusel alcohols being produced. I mentioned this already, but trub presence and wort. Higher fan and faster fermentations will cause more to occur. And also, this is a weird one, but dissolved CO2 has a really big impact on how much fusels are produced. CO2 can restrict fusel formation, which is an odd one, and that we do not understand why, but it almost, with rare exception, it works for all strains. With rare exception, there's some of the Belgian ones that this doesn't work for, but almost all strains it works across the board. Any questions about fusels? Cool. We're going to diacetyl. Now, odd thing on this, and this question is for my own brutal curiosity. I've had COVID at least once that I know of. I don't know if I've had it more than once. It's kind of hard to tell at this point. I got 2 kids, they're germ factories. My ability to detect diacetyl has plummeted since having COVID. I do this test with the students every term where we do a threshold test. So I can actually tell them to what ppm or ppb of diacetyl they are sensitive to. It's a pretty cool test. I enjoy doing it. And I have my data pre-COVID and my data post-COVID. And post-COVID, I am like an order of magnitude less sensitive to this stuff, which is fascinating, frustrating, but fascinating. It also means I enjoy things more because I'm not tasting this thing in things. So like, excellent for me.
Ignorance is
Excellent.
bliss.
Yeah, exactly. Yeah, it's just if I can't taste it, but it also means that if I taste it, I know it's really bad.
Yeah.
Which is actually a good place that we start on this. So what you see here is the rough distribution of diacetyl inside the population based on concentration. So essentially, what portion of the population is going to be very sensitive to diacetyl, be minimally sensitive to diacetyl, all that stuff. So we see, is that the right one? Oh, yeah. So this is a general population. Usually looks something like this. Now here's the weird thing with it, and this is something that I think it's really important that Like if you're going to go and do anything professionally, it's incredibly important. But even as a home brewer, I think it's important to know. Do you think the people who home brew beer are more or less sensitive to diacetyl than the average person in the population?
I think so, yeah. Like,
That was
I think,
that was an A or B question. I don't know.
sorry, the answer is homebrewers are more receptive. And can taste
Okay.
it more.
Do I have anyone who wants to take the opposing position?
Well, I would say statistically, it's going to be like, as long as your sample size is large enough, it's going to be the same as the population.
You would think that, and that's what I thought for a long time too. It turns out, and this makes lots of sense once you think through it. Most people in beer, like or who like beer relative to the average population, we're not great at this.
Oh, okay.
The reason for it makes a lot of sense. So if you were very sensitive to off flavors typically found in beer, do you think you'd like beer?
Well, you might like good beer.
You might like good beer, but the chance that you think beer is a good product or that you enjoy multiple beers is probably a lot less. So there's almost like a self-selecting bias on this, and we start looking at this. We see this with all beer off flavors. The people who are, not so great, people who are more sensitive to these compounds typically don't like beer, and the people who are less sensitive to them tend to like beer. It's almost like a self-fulfilling prophecy to a certain degree. I used to work for a brewery in. I actually don't know if you guys know. How familiar you guys are? They ship coast to coast. Great Lakes Brewery.
Yep.
Are they out there?
No, I'm from Ontario originally.
Okay. So I worked. I think the closest thing to them would probably Phillips. I worked for them, and when I was there, we would do diacetyl testing for all like we go to the cellar whenever we had to go cold crash a beer. All the like I'm not great at it. I'm okay at it. Some of the people I worked with were completely blind to it. But we had one woman, her name was Trish. She worked in accounting, and she was really good at this. She did not like beer. She did not like beer. And we gave her so much beer because she was wonderful at picking out all these off flavors. Like she could pick out like, yeah, that has diacetyl, don't do it. Yeah, that's got that thing, don't do it. That's got this thing, don't do it. And she was sensitive to all of them. I ran her through testing. She was the most sensitive person in the entire building to common beer off flavors. And I used that thing. So I used that knowledge every single day. It was great. So yeah, if you're making beer, and this is why for you guys and gals, like you may not always taste this. This could be in your product, but you may not know it. You could have this in your beer, and like you may give it to your cousin or give it to a friend or something who comes over, and they may think it's absolutely gross, and you can both be right. That's the weird part. Like you can both be correct. So I want to talk about how this stuff works. So this is just kind of like what we saw before. Yeast cells are trying to produce an amino acid, like we saw with fusel alcohols, and we saw with sulfur compounds. They're trying to produce either leucine or valine, and in doing so, they accidentally produce this toxic compound. It's kind of a theme. The yeast cells taking pyruvate. We saw that beforehand. That's the glucose to pyruvate, pyruvate to acetaldehyde, acetaldehyde to ethanol. This is that pyruvate. It's been brought and pushed somewhere else. So this pyruvate goes to a molecule called alpha-acetolactate. We're going to talk about it more in a second. The yeast cell is then wanting to spend lots of energy to then create these two molecules and eventually an amino acid. But sometimes this alpha-acetolactate, it naturally decarboxylates. The CO2 just naturally cleaves off of it. You can't control this. It's going to happen. And that's where we get diacetyl. So if the yeast cell's trying to produce leucine and valine, it accidentally is going to produce some diacetyl. There's no way around it. Ish. So let's just kind of go from the top. If the yeast cell didn't have to produce leucine or valine, didn't have to produce these amino acids, it had sufficient FAN, this pathway doesn't turn on. Doesn't need to. If the yeast cell already has the amino acids, if it has a good diet, like hopefully we do here, hopefully, knock wood. If it has all the amino acids it needs, it doesn't have to make its own. It just takes them from the environment or takes them from the yeast extract that you provided to it, which means that your cells aren't going to produce diacetyl. It's kind of as simple as that. If the yeast cell does not need to turn this pathway on, and this pathway results in diacetyl, we get less diacetyl. All is well. Now, does that part make sense? We're about to build on it, so I don't know. Is that making sense?
I have a kind of related, unrelated question, which is probably super newbie, but so I think this is the same thing in wine that comes from malolactic fermentation, right? But in that case, it's a positive thing.
So it will, the organism that's associated with malolactic fermentation is very hungry for valine and leucine, which is why it produces diacetyl. For wine, especially for Chardonnays, it's considered to be a positive thing. For most beer, it's considered to be an off flavor.
Okay.
And there are low valine requiring malolactic organisms for wine that can go through malolactic without having the diacetyl production.
Okay.
Yeah. So it's a bit of both. It's a good question though, by the way. That's yeah. So here's where things get a little insidious, and I want to do a bit of a show of hands on this part because I'm curious about what the beer scene is like in Vancouver. My own self part of it. Have you ever had a beer where you open it, like you've bought it at wherever you acquire alcohol, and it's just a diacetyl bomb? It just tastes like butterscotch or just like fake butter flavoring. And have we all experienced this? You just put a hand up. Yeah. If you haven't, just wait. It will happen. It will happen. And when it does, you'll probably be thinking to yourself, like, man, how did this brewer allow this beer to leave their facility? Like, how is this person being so reckless that this beer that is completely like riddled with an off flavor was allowed to be packaged? And the truth is, they probably had no idea. Now, for two reasons. Now, one, they could be completely blind. They could be absolutely blind to it. The head brewer at the college, his name's John Downing. He opened up brew pub number 1 in Ontario, which is pretty cool. Actually, the guy's been around. He's 64 right now. He's about to retire in a couple of years. He's not doing 65. He wants to be for like 68 or something like that. Yeah, he's opened up brew pubs all across the world. The guy is completely blind to diacetyl. Completely blind. It's like he knows not to trust himself for this stuff. The other way in which this can come apart is a bit more insidious. And I said we were going to talk about this molecule alpha-acetylactate. Can everyone see my mouse? We're hovering over the alpha-acetylactate molecule. Okay. So if you have a beer and it's finished fermenting and things like that, you're trying it and it tastes excellent. And then say you package it, you put it in bottles or cans or kegs, whatever you guys are doing for it. And then like a week or two later, it starts tasting diacetyl. This is what's happened. What we're going to talk about is what's happened. So this alpha-acetylactate molecule is insidious. It is odorless, tasteless. It is not detectable by the human palate in any way, shape, or form. And when we expose this molecule to oxygen or high temperatures, it breaks down into diacetyl. So if we have a little bit of O2 pickup while packaging, which is going to happen, it's unavoidable, it'll turn into diacetyl. If we've packaged all our beer and we're trying to then re-ferment the beer to carbonate it, it can turn back into diacetyl or revert into diacetyl. A lot of different things will happen. If you're the brewery down the road has packaged a pale ale and then put it on a warm store shelf, which you can buy and then put in your fridge. This can happen. Not ideal. Not ideal at all. Improper storage. It's absolutely improper storage, but a lot of beer is improperly stored, and it's just kind of the name of the game. We're not going to go down that rabbit hole because I have lots of strong feelings about supply chain and who's responsible for that, but we're not going to go down that. Now, luckily for this, and this is kind of the a cool test you can do. And I would suggest you guys do this as well. I know it's homebrew, but I think I know it's just homebrew, and how you look at it. But I'd recommend you do it. There's a test called a forced diacetyl test. Has anyone ever done this test before? You got one person. You're new. You're good. You're fine. So you're over here for me. So yeah, the forced diacetyl test is a way for us to test the beer very easily to make sure that the beer does not have any of this alpha-lactate molecule to it. And the way we do it is really easy. I've given this talk a few times, just called your brewery lab in a mason jar, because that's really all you need for this. You take a small sample of your beer, you put it in like a small 100 ml mason jar. You get a container of hot water, like for breweries, it's fill a bucket of water and chuck the mason jar in, forget about it for a while. You come back later and then you open it up and you smell it. That's it. The heat that we see here, the high temperature, will heat that sample up and will break down all the alpha-lactate into diacetyl. So when we heat the sample up, if the sample now smells buttery, we know it's not time yet. If it smells good, we're good to do cold crash, package, whatever we want to do to the beer. We're fine to do it. It's a really simple test. It takes almost no time. The only thing I have to stress for it is that you cannot microwave the sample. Microwaves don't work. You can microwave hot water and then put your sample in the hot water, but you cannot microwave the sample. It actually causes the diacetyl to chemically react with other things inside the wort, neutralizing it. So it becomes non-detectable. So don't do that. I've had clients do that, and they're like, "Yeah, don't do that." So yeah, diacetyl can be a whole bunch of different things, but it almost always comes down to unhealthy fermentation of some way, shape, or form. Lack of fan, too much fan, can be a bunch of different weird things. Any questions about diacetyl? I think we're good. Okay. I think PSLs are delicious. I'm here for pumpkin spice. There's two breweries in Ontario that, 8 years ago or so were the two biggest ones for making pumpkin, Grand River Brewing and Great Lakes Brewing. I've worked for both. I've made a lot of pumpkin beer. I like pumpkin beer. It's what I like. I'm okay with it. I just drank one. Excellent. I'm all for it. So yeah, why do yeast cells produce phenols? This is a really important question we have to ask first. Now, to kind of get further into this, we can't ask the yeast cells why they do this, but we can kind of infer. And if anyone can learn how to speak to yeast cells, let me know, because I have lots of questions. Lots of questions to answer. But here's the going hypothesis. There is a molecule found in not just barley, but wheat, oats, rye, spelt, quinoa, buckwheat, sorghum, all sorts of different grains, called ferulic acid. And it's slightly toxic to yeast cells. So they want to break it down. And when they break ferulic acid down, it creates a compound called 4-VG, or 4-vinyl glycol, which is the phenol or the spicy characteristic we find in beer. That's the hypothesis here. The yeast cell is trying to simply detoxify the environment. It has this ferulic acid in the environment. It wants to break down the acid and turn it into something that is less toxic, which makes lots of sense. Now, if we kind of look a little bit higher up, what sorts of beers have this kind of spicy tone in them? Like when we think about beers that are phenolic positive, what types of beers are they?
Saisons, Belgians,
Saisons. Yeah.
Saisons, Belgians. What type of Belgians?
like a farmhouse ale.
Farmhouses, yeah. What else?
The lambic, maybe.
Yeah, lambics have it.
Quad.
Sorry?
A quad.
Variably quads, depends on ingredient usage.
A wit.
Wits, that's a big one.
Yeah.
That's a huge one. And then Hefeweizen or Weisens are the other big one.
Oh, but that's not a Belgian.
Oh, now the German's getting angry.
I asked what has phenols. That's
But
Belgian.
you specifically asked about Belgian.
I meant just what spicy beers are there. Okay. If you look at all these wits, lots of wheat. Weisens, lots of wheat. Lambic, lots of wheat. Saisons, lots of wheat. Wheat has a much higher concentration of ferulic acid than any other grain. They all have it. Wheat has the highest, which makes sense when we have wheat beer yeasts that they need a better way to help break this thing down. That's one of the hypotheses as to why we have certain yeast strains and not others that have this. Now, another cool part for this, and this is it's always kind of blows some of my students' mind when I show this. Did we all know that that whales have hip bones? For those that didn't know, we'll take a quick detour because it's a cool thing to show. Whale hip bone. There we go. Whales have hip bones. All of them. Right there. They all have hip bones. Now, why? Why would they have a hip bone? It's because whales at one point had 4 legs. So from an evolutionary standpoint, they come from organisms that were on the land. You want to go into like I taught my son about this a few weeks ago, blew his mind for a couple of days, and he got back into Lego, which is we're fine. Yeah, this is what we call a vestigial, in this case, limb, but sometimes we have vestigial organs, an organ that is no longer needed, that is no longer required. And when something is no longer required over a long enough time period, it's broken down. It's removed, just like the legs of the whales that were no longer needed. When humans have used yeast strains for a large period of time, and they're no longer being exposed to wheat, they start losing genes that are no longer needed, like this gene required to break down or produce phenols. So every single clean yeast we have, so if we're talking like Cali, lagers, even like the English strains, they all have the gene inside of them to produce the spicy tone, but it's broken. It's damaged. It's been minimized in some way, shape, or form. It's because it was no longer needed. It was no longer really being exposed to these stressors, no longer exposed to this wheat as a stressor. And the yeast strain, over a couple hundred years of use, it broke. It was okay to break, so it's still broken. That's it. But almost every single strain does have the genes still in there. It's kind of a cool thing. I find that's kind of useful to help us understand kind of why the yeast cells or how the yeast cells function. Now, when you're looking at how much, if you want to dial in your clove or you want to get more or less, it's a bit complicated. You can start looking at, how much wheat you're using if you're for wits, saisons, things like that. Especially for wits, if you're using torrefied versus puffed versus malted wheats, like the type of wheat will impact how much spice characters it comes into the final beer. With the malted ones typically having less, a lower spice characters than if you're using, say, raw wheats or things like that. So different base malts will have a big impact. The biggest impact, though, is going to be strain selection. There are some yeast strains, like our Weizen 2, that just had, sorry, not Weizen 2. We killed Weizen 2 as a product. Weizen 1 has much more clove characters than my favorite Hefeweizen strain we sell, which is called Uberweizen. We have about 4 or 5 different wit strains. They all have different clove profiles, just based on how much of this gene is active and expressive. So like the genes are really going to be the thing or the strain selection really going to be the thing that determines how much clove, how much phenol characteristics you're going to get. That's the easiest one. Now, if you want to get really into the weeds on this, you can, and we have it right here. This is a part of a data set that we generated with esters on the left-hand side and phenols on the right-hand side. And you can see that certain yeast strains produce way more phenols than others. We're not going to go through it right now, but if you do want to kind of go through it, this is information we have available. You can find this information in our yeast cell flavor guide, which you can download online for free, it's a pretty cool resource. It's one of these things that if I was geeking out and trying to make beer when I was like home brewing, 15 years ago or so, I would be all over this thing. But I was the guy that bought a microscope and he was a tomater because I thought it was cool. So it's not for everyone. Andrew, when they're talking about are you down the rabbit hole, that is the rabbit hole I chose to go down when it comes to equipment. Not for everyone. Not for everyone. Yeah, definitely not for everyone. And Thanks, Leonard. Yeah, Uberweizen is my favorite lager strain. Sorry, Weizen strain we produce. Period. Time. That thing's awesome. So yeah, we have this also ferulic acid isn't the only acid like this we see. We also see cinnamonic acid and coumaric acid. You really don't want cinnamonic acid. That creates like styrene, which is kind of plastic. And if the coumaric acid will turn into a thing called 4-vinyl phenol, which tastes medicinal. It's really not pleasant. Luckily, cinnamonic and coumaric acid are very low concentration set of most grains. But if you do use like some odder grains or the ancient grains or just kind of unprocessed grains, you might get higher concentrations of these too, which might cause some off flavor. So if you are exploring that as a ingredient usage, just be aware that that might be something that comes up as an issue. So yeah, that's sorry. That's the bulk of all the different kind of off flavors we wanted to hit, or I wanted to hit. If you're looking at kind of the best practice for controlling all of these, healthy yeast is your number one friend. Like just making sure the yeast cells are happy and healthy. That's going to be the best thing you can do. Just like humans in unhealthy yeast cells act erratically and we don't understand what they're going to do. So if the yeast cells aren't healthy, it's hard to say what's actually going to happen. Making sure you have the correct pitch rate. Correct pitch rate's a bit of a black box. That's a separate presentation. Separate presentation. But as a general rule, it is always better to overpitch than it is to underpitch. Overpitching, like if you think of trying to feed people, overpitching, like if you have a table for a food for 20 people and 30 people show up, everyone gets fed, but everyone's a little hungry. It's okay. It's not ideal, but it's okay. If you have a table for 20, it's like 20 people worth food for 20 people, but only 10 show up, each person's going to be bloated, distended, and there's still going to be food on the table, and you got to clean up more, and it's going to be a mess. It's far better to overpitch than it is to underpitch in almost every single situation. I can't think of a situation where it's not. Proper nutrition is going to be huge, like yeast lightning or yeast extract, Saccharomyces, things like that. These are all very useful things. And just avoid contamination. Like you got to make sure your stuff's clean. If you have lactobacillus, pediococcus, bacilluses, things like that in your beer, all the things we talked about today are all every single organism has its own pathways for metabolism. They're going to do their own thing. They're going to produce weird flavors, and I couldn't tell you what they're going to do based on each one. It's going to be different case per case. So when it comes to you as like what should a home brewer do, I do have some thoughts, and this is one of the things I want to kind of just showcase to it. So one of the best things you can do as a home brewer to ensure the yeast cell has enough energy to kind of break down all these different things is to do a yeast starter. And I would encourage you to do a yeast starter for a handful of reasons. Mainly to give it more oxygen. Now, we started from the top at this kind of asking, like, do yeast cells know that we're alive? Do they know they exist? And they don't. They have no idea. Like they're not trying to appease us or make us happy. So I want to ask a similar question. Do yeast cells like making alcohol? We have one person shaking their head.
I mean, they do make alcohol, whether they like it or not. We're ascribing emotions to a.
They prefer
simple.
consuming oxygen, and then once the oxygen is kind of run out, then they actually start producing alcohol.
Exactly. Yeah. So
the alcohol is like close if they're going to be done, and then they're going to be dead, right? Once they're done consuming the sugars, so then, right? Is that right?
You're getting there. So
okay.
I want to kind of give like an evolutionary like thought process as to why we believe yeast cells even do this. So if you look at a lot of different organisms, molds, bacteria, things like that are found wild in the environment, like at 0.5% ABV, they all die. Like they're not alcohol tolerant. The fact that yeast cells and lactobacillus are alcohol tolerant is very unique, is incredibly unique. So the going hypothesis from an evolutionary standpoint is that if the yeast cell produced alcohol, it was simply available carbohydrates. You know, they'd land on an apple, they'd produce 0.5% ABV on the fruit, and now that entire apple is theirs because nothing else can consume it. Now, as they're doing this, they're exposed to large amounts of oxygen. Large amounts of oxygen. Anyone know how beer has been historically brewed? physically, like what sort of historically fermented, let's say for the last 3,000 years, like what type of vessels were used?
It was in like a
Typically-
large tray.
Yeah, typically open
Trays.
vessel.
Open
Open
fermenters. Yeah.
vessels, open vessels, open fermentation. So if you are, from an evolutionary standpoint, if you're a yeast strain, are you used to open fermentation or are you used to closed fermentation?
Open.
You're used to open. Now, an open fermentation is going to have tons of oxygen access, tons. Also, on top of this, oxygen, when the yeast cell is exposed to oxygen, for every molecule of glucose it consumes, it produces about 18-fold, 18 times the energy it would if it's just going through anaerobic. A lot of the issues we talked about today, acetaldehyde, diacetyl, a lot of sulfur compounds, fusel alcohols, all of these are produced. So we saw, I mentioned the NADH molecule a few times. I was doing that intentionally. When we expose the yeast cell to oxygen, NADH levels spike, which means they have enough energy to clean up all these off flavors, all of them. If the yeast does not have enough oxygen, we do not have enough of any of these. Like we are more likely to get diacetyl, acetaldehyde, sulfur, everything, fusels. We're going to get more if we do not expose the yeast cells to enough oxygen. So this is why I'm saying you need to expose your cells to oxygen, not for a cell count standpoint, not for the cell, like, you need to cause the yeast cells to grow. You need to get the yeast cells to have ample access to oxygen before you start fermenting. That's the goal. Now, for people, I don't recall who, you're over here for me. So you aerate your wort. That's excellent. Do it. I strongly encourage you to do that. Like, keep doing that. But the goal of wort aeration is to provide oxygen to your yeast cells. That is the goal of aerating the wort, is that we aerate the wort so that when the yeast cells hit the wort, they can start fermenting. The unique thing about you guys, but for scale, is that you can aerate your yeast cells. You can make a small 1 or 2 liter culture, and you can put your yeast cells in there with like 500 mils of wort from a previous brew or something like that, and you can aerate the cells right before you brew. If I want to do that on a commercial scale, I would need a stir plate that is moving like 100 liters of liquid. That doesn't exist. The magnet on that thing alone would be a health and safety hazard. Like if someone has a pacemaker, you might kill them. Like it would not be good. But for home brewing, you can absolutely do this. Like home brewing, if you can use a stir plate to agitate and get more oxygen into that culture much more easily than almost anybody else. And I'd strongly encourage you to do so, because you're going to get more oxygen into them because you have the more NADH, more energy reserves, healthier yeast cells. Don't do it for long. We're talking like 2 to 6 hours before pitching. Like just a couple hours beforehand, assuming you have enough cells. If you don't have enough cells, different story, 24 hours. But if you're just if you're just brewing that day, put them on a stir plate, get them going, add oxygen to them, let the cells start ripping, give them the nutrients they need so that they're going to have a healthier fermentation. That's my 2 cents, at least.
I have a
Option.
question with yeast starters, if that's cool.
Yeah, sure, shoot.
So whenever I make a yeast starter, I make it like a couple days ahead of time, because what I'm really have always done is I do it to increase the cell count more than to introduce oxygen. And then I cold crash it and pour that beer off, and then I like pitch it day of. Is it like that's sort of counterproductive to what you're saying? Like it's not the
not necessarily. So much like a battery, yeast cells do have an oxygen battery in a sense. Like they do have the ability, they're not storing oxygen like intracellularly. That's not how that works. But they'll produce a lot of sterols, a lot of fatty acids, all their lipids that are inside the cells that will allow them to, very, very easily tolerate an anaerobic environment or a minimally aerobic environment. Just far, far better than they would otherwise. So like that's a good protocol. I would not tell you to change it unless you were still having issues with diacetyl or things like that. Now, the other flip side to this is that, and this is, when I deal with this with commercial clients, where say the brewer is aerating their wort, but the system they have for wort aeration means that they cap out at like 5 ppm of O2 and they need 10. What do? This is where yeast nutrients come into a lot. I know I said yeast nutrients a lot. It's super useful. Like I cannot emphasize how useful it is. Like the day that we kind of got our yeast nutrient locked in And we started using it we were using it internally for our own production for about 1.5 to 2 years before we ever said let it get out in the wild, by the way. Like we worked on that thing for a long time. I'm really happy with that product. Really happy with it. Instead of having the yeast cell having to produce valine, we just give them the valine. Instead of having the yeast cell having to produce these certain amino acids for growth, which causes fusel alcohols, we just give it to them. We can actually reduce the amount of oxygen that the yeast cells require by just giving them more yeast X, giving them more nutrition. That's kind of an edge case as to how to balance it out. It's not as clean. Like I mean, like the reason for it is not as clean, but the impact can be a very clean beer if you can't get enough oxygen into the product. I wouldn't change your protocol unless you're unhappy with it. That's the other part to it.
Oh no, everything works. I just, it's always like at least 24 to 48 hours before I brew. I do not 6 hours, you know. And
yeah, I'm gonna guess that you're also cold crashing the cells too.
Like yeah, cold crashing and then pouring off that beer, because that's not what I want to add to my beer. You know, when I'm making a lager, I'm making like a 3-liter starter, and I don't want to add 2 liters of dry malt extract lager to my beer. You know,
no, that is the right call. That is absolutely the right call. That's what I would be doing. If I didn't have a yeast lab, I just go and grab more. That's exactly what I would be doing.
Yeah, and I mean, pitching enough yeast right from the packs, it gets expensive, right? So making yeast
exactly
like a cost efficient way of doing things. So that's why I do it. So
yeah, I'd be doing the same thing. Like this is oh man, if we go back in the Wayback Machine, I remember going on kind of dodgy US stores at the time because that's all I had, shipping in vials of White Labs products from the States into a mailbox somewhere in Kitchener, Waterloo, going to go drive it and getting like 4-month-old high temperature lager yeast and having to grow it up from that. And like, oh yeah. And it was like $20 or $30 a vial because of everything that went into it. It was a mess. Yeah, I would do the same thing. Like, yeah, like I would doing starters just for a handful of reasons. For this reason, for making sure it has proper aeration, and also just to get more cell count. The other part for this, and this is kind of like a good housekeeping thing, is it is always better to pitch more cells than it is to pitch less cells. Like if your option is an overpitch or an underpitch, always overpitch. Always. It's not even a question. Always overpitch. Underpitching will cause off flavors. Overpitching will cause the flavors to be less intense. Like the flavors will be neutral, not negative. So it's always better to have kind of boring beer than it is to have bad beer. Yeah. We're gonna, if you have more questions, we're almost like 2 slides left. All I have here is like, if you guys want more information on this, like one of the big things that we try to do as a company, I try to do for both. When my first hat of Escarpment Labs, the second hat is Niagara College, we try to teach people how these things work. I hope today's kind of shown you guys that like, there's a lot of information out there. If you want to understand how yeast cells function or how certain things for the brewing process function, like we got resources for you. We have a thing called the yeast knowledge base. It's free. It's online. If you just Google it, Escarpment Labs knowledge base, you'll find this, and you can find all the different articles we have when it comes to certain yeast strains, like how certain things work, troubleshooting advice, all sorts of different things. My one business partner, Richard, one of the ways we kind of frame this is like, what information would we have wanted to know when we were starting out commercially or when we were home brewing? And we try to make it because it would have been handy. And yeah, we have over 50 hours of 50 hours of YouTube content online. This will be added to it once we get it. So if you want to go into certain things, we have a whole series on yeast basics and yeast basics 2, and like how to make non-alc beer. There's also different like kind of niche topics if you want to get really into the weeds on the really, nitty gritty on this stuff. We got tons of content on there for you if you want to explore and find it all. We got lots. Yeah, I think that's all the things I wanted to cover. I think I covered everything that you guys that were kind of asked. Are we good?
Yeah.
Okay, cool. What questions do you guys have? None is fine. I won't be offended. It's all good. It's been a long day for me. I'm fine. I'm curious on this part. This again, some of these questions are just for my own self-interest. How many different yeast strains do you guys typically use? Or how frequent are people brewing? Maybe is another question on this.
I was until COVID hit. Well, I guess actually, and even for the first year of COVID, when we had somebody living with us who was drinking a lot of beer, I was brewing a batch a month, and so I had about 5 or 6 liquid yeasts in rotation.
Okay.
I had a Kvike, a Belgian, a couple of different ale yeasts, and I was keeping them all pretty healthy. But since then, I think this year I've brewed twice, and so I've not been able to keep any yeast batch. I was doing the brewlosophy method of doing a big yeast starter and then just peeling off a third of it and keeping it in a mason jar and just reusing that, and it was working really well. But now I have to actually go buy my liquid yeast when I want to brew, and unfortunately, we've lost several homebrew stores in the last couple of years, and so my selection of liquid yeasts is really getting shorter and shorter, which is disappointing. I don't want to have to mail order my liquid yeast. That's too much planning.
Yeah, no, I hear that. Yeah. How often else are there other people brewing? I'm curious about this.
I brew a couple times a month, usually, like say 3 batches over the course of 2 months, more like.
Right.
And usually it's like 2 lagers at a time, because my freezer does like holds 2 carboys perfectly. So lagers, because they take a lot longer, I do 2 at a time, and then I make an ale, and then I go back to 2 lagers, and it's sort of been my routine for a while.
All right.
Do you have big parties then, Chad, to get through all that beer?
No, I definitely drink a little more than I should, but I like to give a lot away too. So
You just wander down the street, he'll drop a 10-foot or a 30-foot hose down to the balcony.
yeah, you know where I live, Steve. Come on over, have a beer.
Yeah. I've got 7 beers on tap right now at home, but I've got no one here to drink them. So
Well, you're also having a party on Saturday, so we'll fix that.
yeah, hopefully that'll help. Yeah.
Halloween.
Yep. Halloween themed 80s party.
Nice.
I used to do this. Well, I have done the same, harvest off the starter thing. I was told to clean out the kitchen fridge a couple weeks ago. I found some things growing that I'd forgotten about in the back. A couple-year-old mason jars. I cracked a couple and reached up and shook my hand and said hello. So that yeast did know I was alive. Yeah.
This is about a year or two ago. My parents were clearing out some stuff in the basement, and I thought I had, over a decade ago, cleared all my brewing stuff from their house, and they found a few samples in the back of the fridge. I'm like, oh good Lord, oh God. It was pretty.
And you opened them for science, right?
I did. I played with them because I was curious. Everything was dead. It was all dead. Because that being said, we have isolated Brettanomyces which is a type of yeast, from, I want to say it was like 60-year-old beer, or like 38-year-old beer. Like we've isolated some stuff from some really old cultures. Some organisms will survive. Some of them are survivalists.
See, Andrea had a question in the chat. Did you want to speak to
Can
that,
you
Andrea?
resurrect dormant yeast as well as bread yeast like sourdough or not survive? Oh, okay. This is a good question. So resurrecting a culture is just trying to get my thoughts in a line so I can make sure I say everything I want to say.
I'm asking because I know already with my sourdough culture, like it takes a beating.
It does
So
take a beating.
I
It will-
feel, I
it will take a
neglect
beating.
it, and then I feel like I'd probably be the same with other yeast, but hopefully not. Anyway.
So yeah, the nice thing about brewing yeast is that like you can be a bit more neglectful on it as long as you do a starter with it before you use it. Now the issue with that, and this is the point just to emphasize with it, it may not be the same as it was when you used it last time if you do this. So as the yeast cells are dormant, as they are not fermenting and things like that, they are dying, but they're also mutating a little bit. Now, this is not the source of mutations, and it's not a way that I'd recommend pushing artificial selection by any means, but you can damage them a little bit. And I think damage them is the right way to look at this, not mutate. I take back what I said previously. So when you do this, like the culture you get back on the other end will be very similar to what you started off with, but it may not be the same. Now, for the same reason, like when we're growing our yeast cells, I can't recall the interval that we do. I want to say it's every 2 months or every 3 months. We'll take all our core strains and re-streak them from a frozen starter. So it's a frozen stock culture. That's at -80 degrees Celsius. Like it's frozen away. We don't have to worry about it. But it means that all our batches have the same age. Like we're growing the same strain, but we're not going from batch to batch to batch to batch to batch. And the cell's not able to mutate and change from batch to batch to batch to batch. So it's consistent. Now, when it comes to sourdoughs, I know if you look at the world of bread, like commercial baking, there are kind of two trains of thought. The more commercially savvy, like your Wonder Breads and things like that, they are buying yeast in bulk from large facilities, and that is how they get their yeast. And that thing is not allowed to drift, because like if it takes an hour and a half or 2 hours longer for proofing, it's not as useful as if it was a shorter period of time. And like the weird thing is, like for some of the bread yeast manufacturers, say the bread proofed in 15 minutes less, that actually may not be a good thing for them. It may actually hurt their throughput. So the bread yeast world is a very different world for beer, because everything has to kind of be locked in. You then have more of the artisanal, like sourdoughs and things like that, in which case, like, your variability and variance is completely fine and usually embraced. And that's more what you'd be doing for something like this. It's like you can resurrect all of them, but just be very aware that it may not be exactly the same as it was before. And that goes for kombucha. That goes for like if you have a lactic culture for pickles or things like that, like anything like that, it will happen. We do have some information online in bread making, by the way, if you do want to go into that. I think it's on our blog. My one business partner is really into bread. Like he teaches courses on how to make sourdoughs. I'm not a baker. I dabble in making pretzels and things like that, but I'm not the baker.
That's awesome. Thank you.
No problem. Does that have any other yeast? Oh yeah, we got enough yeast lightning nutrients after opening the 20-gram pouch. Use 1 gram. Yeah, just put it in the fridge. Yeah, you don't have. Ideally, you keep the thing as tight as you possibly can. But yeah, you can just put it back in the fridge. If it starts getting, the issue with any sort of yeast extract is if it gets access to moisture, it can mold. So as long as you keep it devoid of moisture as much as possible, that's great. We've had people put the yeast, so the little container, in a Ziploc bag, and then really make sure it's devoid of oxygen and no moisture. And that's if I was doing that, that's what I do. I usually at home transfer them into like test tubes and things like that, but I don't think most people have access to those. We do, but I don't think that's a common thing yet in your house. Cool.
All right.
I think
Thank you very much, Nate. That was an awesome presentation.
No problem. I hope you guys understand how yeast cells work a bit better. And yeah, if you have any questions, let us know. We're glad to help. Yeah, cool.
Yeah, thanks, Nate. I think this is one I'm going to rewatch, because there was a lot I caught, but a lot I didn't catch, and I think a rewatch is necessary to really fully absorb everything.
Yeah, absolutely. Yeah, and this is some of the things I say to a handful of my students. And one of the benefits of online content is that you can rewind me.
Yeah.
If it's a lecture in person, you cannot rewind me. I don't do that. Awesome. So yeah, I think I'll sign off, and I'm gonna go to bed.
Yeah, good plan.
Yeah. Thanks very much for staying up late.
Yes, thank you for your time.
Yeah, we
really
we
appreciate
really
it.
enjoyed it.
No problem.
Thank you.
Have a
Awesome.
nice-
Thank you, Nate.
No problem. Have a good rest of your meeting, and yeah, cheers.